You see the IP4 version 4, IP version 4 or IPv4 is comprised of 4 numbers: 127.127.1.1.1. 4 numbers: 127, 1, 1, and 1. So the 4 numbers. Each one is ranges from 0 to 25, 255. Each one means, in order to get to 255, imagine a byte. Okay, a byte is 8 bits. And 8 bits is that, if you can, that means the range is from 0. It's either all bits are zeros or all bits are 1. That means it goes from, so if you, I think I talked to you about this before, right? Imagine, so we have 4 numbers. Each one of those numbers is a byte. Each byte is 8 bits. That goes to the range of 2 to the power of 0, 2 to the power of 7. Because it starts at 2 base bit 0. 0 through 7 is 8 bits. So each bit has got 3 things: base, which is binary, right? One base 2 is binary, 2, and then the power, which is the location. This is bit 0, because we're going from right to left. Bit 0, base is 2 to the power of 0, and then the value for that bit location, it could be 0 or 1. Okay, so if 2 to the power of 0 is 1, if the value is 0, then it's 0. But 2 to the power of 0 is 1. If the value is 1, then you have 1. 1 times 1 is 1. Then you go to the next bit, 2 to the power of 1. So 2 to the power of 0, 2 to the power of 1. 2 to the power of 1 is 2. If the value is 1, then you have 2. You already had 1, so now you have 3. You see? 2 to the power of 2 times, assume that all bits have values 1. Then you have 2 to the power of 2 is 4, times 1 is 4. 4 plus 2 plus 1 is 7. The next one, 2 to the power of 3 is 8. 8 times 1 is 8, plus 7 is 15. So now with 4 bits, 0 through 3, okay? 2 to the power of 0, 2 to the power of 3, now we have value 15, if it's all the values are 1. So you just add up all those, assuming that all values are 1, then 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. If we add up all those numbers, the values are 1, the total is going to be 255. That is the range of values that you can get for the base byte of the IP address. So imagine you have 4 bytes, right? And then each one goes from 0 to 255, 0 to 255, 0 to 255. Imagine how many total of addresses can support. You see, the other thing is this. You say IP version 4 has a limit of 4.3 billion addresses. If you take, assume that, you have 4 numbers, each one goes range from 0 to 55, assuming that it's 255 on each one, imagine how many addresses going to be. That is 4.3 billion addresses. But we needed more. We needed more than IP Internet Protocol version 4. So we developed the IP version 6. Okay, look at the IP version 6. IP version 6, it uses 128 bit addresses. That's how an IP version 6 looks like. That's what's just an example of an IP version 6. That means the range of addresses that can be supported under, IP6 is 340 undecillion addresses. Okay, this is actually the this is the actual example. You see 2002 colon dot colon 1 colon dot dot. That's an address under IP version 6, IP6. And I sent you this article you can read, but I told you the main things. So going back to our example, so we have IP address family INET version 4, IP version 4, and IP address family INET version 6. And when you do a bind, you're binding to that address space. You see in this client server communication, you do a system call called bind. That's what it takes your address and bind it into that address space. Bind means like shake hands, that's it. As I mentioned, you call listen, you get server gets blocked until the client connects. Server listen continues, accept the client, and then now you have a TCP/IP connection in client server. Okay. Type communication type socket stream, which is TCP/IP. Another form is the socket datagram, DGRAM. Datagrams are like, a telephone, you have to connect. So you do a connection, you establish the connection first before you have any communication, right? But there is another way of communication. It's called socket datagram. And I've used this in one project in the past, where you drop is like a mailbox. You drop the mail into the mailbox, and then you leave, right? But your mail gets delivered to the place. That is the type of example of datagram. And what happens when within the software datagram, you're going to get an, I just gave you a post office as a real world example, but in the communication environment protocol, when you use UDP, what happens is that you're looking for acknowledgement. And if you don't receive the acknowledgement, in certain time, then you do what's called retry. You're going to retry, and then you're going to retry a few times, 3 or 4 times. If you don't receive the acknowledgement, you just abort. Okay, so protocol value for the internet IP, which is 0, same number would appease the protocol field and IP header of the packet. Just for your information, I work on a project that, I don't know if you're familiar with communication under Java. One of the communication protocol has it's called RMI. And for one, it wasn't a very large application, it was a small size, but it will do what the protocol, the communication base will do work for a larger number of clients. So what's RMI, Java RMI? What RMI does is that basically you build a message and then you send it across the net. So what happens is marshalizing the object, and then on the other end, you do unmarshalizing the object. Okay. What I did, this was one application. And what I did, I converted this RMI to TCP/IP. And actually underneath of RMI is TCP/IP. But RMI is, the layers are built on top of the TCP/IP, okay? Java is slow anyway in terms of, compared with other languages, but then you'd have this layers building, like I said, marshalizing, unmarshalizing, all of that, packaging it. But anyway, I just directly from the application, underneath, as I said, is TCP/IP, but I went from the application directly using TCP/IP calls. And the goal was for me to find out what's the performance of this application would be if you use an RMI versus TCP/IP directly. And I learned that it's much faster when I run the application under TCP/IP directly. You see. Okay. So the other thing is a set socket option. Okay, we're going to look at an example of this. The bind. So let's bind, it's got bind system call, it's got all this set of, so you have you're passing a socket file descriptor, you have a structure socket address. Yeah, it is a pointer to the socket address. That variable name is adder, right? And then the third parameter is the address length, which is a type of socket length T, which is in the socket.h library file. Okay, so let's see what bind does. After creation of the socket, bind function binds the socket to the address and port number specified in the address. In the example, we bind the server to the local host. Hence, we use in address any to specify the IP address. So we bind its server to the local host. The way I would say it is that it takes your address socket, which is an address and port, binds it to an address space defined by an address family. I talked to you about listen. We're going to see an example of this. Connect on the client side. So the code here is the server side code. Okay, so let's see how that works. we have a server file descriptor, new socket, so all those variable name of type int. You have an address which is of type socket address in, and this socket address in is under this. You see, you have system/socket.h. Okay, so it's in there. If you go into that file, you will see what a socket address in data structure look like. And okay, so we do all this. We have a buffer, we have a length, and we have a message. Is a pointer, hello, and pointer to a pointer to character, which makes it to the address of the first first character. And once again, you know this, right? There is a pointer relationship to an array. But when you're defining in a string like this, you cannot change in any character. If you do, you're going to crash. Because when you're defining a string with the pointer character, it only puts it in a read-only memory space. Read-only memory. And then you're trying to change something in the read-only memory space. And that's going to not accept, that's not acceptable. But if you have an array of 2 dimensions and you're defining hello, actually the 1 dimension, if you have 1 string, call it. I'm assuming that we have 3 strings, you know, but if it's 1 string, you can have an array of how many letters, whatever it is. In that sense, if you use just an array subscript array, you can go ahead and change it during your programming. That's no problem, okay? Now, creation of the socket and file descriptor. So what we do, we make a system called socket. We're going to use an address family inet, which means that it's the socket and port. And we're going to use the type to be socket stream, TCP, not UDP. TCP, UDP, okay? So we're going to make a system call, and that returns to us a server file descriptor. So there is checking for if it's 0. If it's 0, that means it's a failure. And we're going to exit. Otherwise, we're going to set the socket options. Over, you know, options are, you know, you're taking, you know, socket option, reuse address, you pipe it into basically concatenate. You're basically taking those 2 options and put them together, what the result, and then pipe it to, you know, SO reuse port. So the address and a port. And then you're passing the address of option. What was the address of option? Option is equal to 1. If you look at it at the beginning, it's int op is equal to 1. And so we pass the address of 1. Okay, so this is how we set the socket option. So when you do a, you know, when you do a socket option, SO reuse address and the port, that's the ORing. You're ORing those 2 things together. This is a bitwising OR, right? Bitwising OR, okay? And then you set something, so you know the address, and then what was the address? Address is the socket address in. That data structure in under in is got all this family. So you set them up, right? IF, you know, what's the family? What's the, you know, there's a data structure, a struct under. So you have a struct socket address in, which is address. And then underneath, you have another struct, which is send address, and then dot. Then you have the element s underscore address, and you set it to be any address. So if you look at if you look at this socket address in underscore in, you see all those. You see the struct and the substruct and everything, all the elements. Okay. So the next thing we do is, so we made this socket connection, we did we made the socket call, we made the socket option. The next thing we do a bind. You're passing the server FD, which is you get it from the socket call. You pass the addresses and size of the address. So you're binding the address space to you see the file descriptor server of this socket. You see, you did it to the address family inet with the type socket stream. What is you have to see what is defined as the address family type. Address family inet. It is defined in it is defined in the inet. You see that net inet.h/_in. So you will see, and the port we want to use is 8080. And you see that you will see what address family inet is defined. So it's either IP version 4 or IP is an IP, you know, is an address family inet. Okay. And so the next thing we do, we're just going to take the next thing we do is going to take accept. We're going to make accept system call. You see everything, you know. By now you get blocked on the listen, but then you have to accept, and the next thing you do is that read from a message. So read message. I think yes. Read, you read and then send. You see read as a receive and then send messages back and forth. Okay, so you see all the system calls within this server side of the socket communication. And then you have this client side. You see, there were only, in the diagram, you only had 3 main system calls to make. You know, socket, 4 actually, socket, connect, and send and receive. You look at the example, you see you do a socket at the beginning, and, you know, and then you do a connect, and then you do send and read. Send and read messages, okay? So I will send you this to try and run it. So remember that you have to bring up the server side first and then have the client just connect, okay? This is only one client and one, I mean, of course, there's one server and then there's one example of client that you need. So at this point, I'd like to give you, you see, you can compile GCC client.c, server.c, and show you what if you run it, you should expect to see what messages you get on the screen, okay? So at this point, I'd like to give you a 10 minutes break so I can get my voice back, and you get the rest too, all right? So I see you in 10 minutes. When I come back, I'm going to talk to you another IPC method called the pipes. So we want to know how processes communicate through pipes. That's the next topic. Hello, everyone. Welcome back. So I'm going to talk to you two things, and then we finish for the day. So I'm going to talk to you about pipe system call, and then I'm going to introduce you. Not introduce you. I'm going to sort of, you may already know, or you may not know, but it is important to know how the number system works, because sometime soon I'm going to introduce you to some, assembly language code. Not too significant, but enough that you be able to do small problems. Okay, so we have covered sockets, communication, shared memory, and memory message queue, and now pipes. Okay. So how are we going to make pipe system calls to have to communicate between processes? Okay. Okay, so a few things. So a pipe is a connection between two processes such that the standard output from one process becomes the standard input in the other process. In Unix operating system, pipes are useful communication between related processes, inter-process communication. So pipe is a one-way communication only. We can use a pipe such that one process writes to the pipe and other process reads from the pipe, okay? The pipe can be used by creating process, used by the creating process as well as its children. For reading and writing, one process can write to this virtual file or pipe, and another related process can read from it. So we're gonna, so the one process writes to the pipe, other process reads from the pipe. It opens the pipe, which is an area of memory that is treated as a virtual file. If a process, I'm looking at the third bullet, if a process tries to read before something is written to the pipe, the process is suspended. Means suspension means it gets blocked until something is written. Because the process tries to read, there is nothing to read. So it gets blocked until something is written to the pipe. The pipe system call finds the first two available positions in the process open file table. Just get familiar. I'll show you an example, and allocates them to the read and write end. So this is what it looks like. And process writes, process reads. So read and writes. Okay, so two positions, 0 and 1. So you have an array of two elements. That's the pipe. You read from the index 0 and you write into index 1. Okay. So let's look at an example. Pipes behave like FIFO. First in, first out. Like queues, right? Queue is a FIFO. Pipe behaves like a queue data structure. Size of the read and write don't have to match here. We can write 1212 bytes at one time at a time, but we can read only 1 byte at a time in a pipe. We can write 512 bytes and read 1 byte. Excuse me. Okay, let's look at the example here. So what we have 3 messages, pointer to character each one. Okay. And so we're going to do a char in buff message size. So, okay, a buffer for message. And then you have an array of 2, and I is a variable. So then you're making a system call. That's pipe, right? You make a system call. Look at the beginning in the header file. So it must be in the Unity standard and .h file, or actually a standard IO. Pipe system call. So you make a system call pipe on the array, and then it is less than, okay, so if it returns less than 0, is an exit, you don't continue. Otherwise, you're going to write. You're going to write to the pipe. You know, the write, read system call, open system call, write system, all of that. But in this case, you're going to write to the pipe. Message 1 with the message size. So you're writing the first message to the pipe. Remember, to this picture, you had the process uses the index 1 of the array to write. Index 0 of the array pipe is to read. Okay. So then, okay, so you write 3 messages, one after the other, and then you're going to go walk through this loop and read pipe. So what do? The read, you read, the picture says 0, index 0. You read on the pipe index 0. You write to index 1, read to index 0. So you walking through 3 times and reading pipe index 0 3 times, and then you one thing puzzled me, you know, in this thing, and I'm going to ask you to try it. It was a while back that I did this. One thing is said. You said that we can write 512 bytes at a time, but we can read only 1 byte at a time in a pipe. So our message, you know, we wrote the message 1, message 2, and message 3. We wrote those, And message 1 has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's got 15 characters, message 1, 15 characters, message 2, 15 characters, message 3. So when we did write, we made the write to index 1 of the pipe. So message size, okay, we wrote those 3 messages, and then we are reading. So we walking through the loop 3 times. The read, what's going to happen? The read is going to read 1 byte at a time. So you read pipe and you put it into in buffer, the message buffer, and then you print in the message buffer. You know, the printf function is the C function where you describe the format is a % space string / new line, and then in buffer, okay? So in each case, we wrote 3 messages and read 3 messages. So very simple, right? Very simple. Parent and child sharing a pipe. So we use fork, right? You have a parent process, you do a fork, and if you do, depends how many children you want, you basically create children. Each child is a process. So we use fork to generate processes, and then file descriptors remain open across child process and also parent process. Okay, file descriptors. We needed file descriptors. What was our first descriptor? We write to the pipe. We made a system called pipe to generate P, and then we wrote to that to establish a pipe, and with 2 ends, 0 and 1, we use 1 to write and 0 to read. And here, so the parent process, file descriptor 0, file descriptor 1. Look at this this other thing here, which is the example shows. It's just the name is different. And our example was an array P of 2, and here is the file descriptors. There will be file descriptor for read, and 1 would be for write. Okay, so in this parent and child sharing a pipe. So this is the look. So we have a pipe, okay, and then we have what happens, the files could remain open across child process and parent process. So you have a parent and a child. The file descriptor 0 and 1 open to parent, this 0 and 1 parent open to child, and they do. So let's see how the code works. So we have, again, 3 messages, and we have a buffer. Okay, so an array of 2 process ID n bytes. So we make a call, system call on an array of 2 elements, so to establish a pipe, and then we call the fork to generate the child. That returns PID if it's 0, less than 0, and 1. So if it's greater than 0, it's the child, and we're going to be good. So we're going to do, actually, if it's greater than 0, it's the child. If it's less than, what was it the fork does? is 0, -1, or, and 1. Oh, 0 is the child. 0 is the child, 1 is the parent, and then -1 is just, it didn't generate anything, it failed. Okay, so PID equal 5, so we're writing to the index 1 of the pipe. So we wrote 3 messages and wait. So if it's greater than 0, we're going to do this, write, and then wait. And then otherwise, if it's not greater than 0, that means, so we're going to do read. We're going to go and read on the index 0. As long as we can read, then we're going to print that information to the buffer. If n byte is not equal to 0, we exit 2. So once again, this is a while loop with the 1 statement. So it's going to finish the while loop and then call the if n byte is not equal to 0, they otherwise finish reading. Okay. Here explains how it works. So the output is this. But why does it hang? You say you read it and print it out, and then it says it hangs. Program does not terminate, but hangs. Okay, so let's see what's going here. In this code, after finishing reading, writing, both parent and child block instead of terminating the process. That is why program hangs. So when the parent writes, the child reads, and then they block, because the pipe is still open. Okay. After finishing reading and writing, both parent and child block instead of terminating the process, and that's why program hangs. This happens because read system will gets as much data as it requests or as much data as the pipe has, whichever is less. So we get back to this. This happens because read system gets as much as data request or as much data as the pipe has, whichever is less. If pipe is empty, and if pipe is empty, we call read system call, then read on the pipe will return end of the file. Okay, so if there is nothing written to the pipe, we call read system call, then read on the pipe will return end of a file. That means it returns 0. If no process has written, okay, if some other process has pipe open for writing, read will block in anticipation of the new data. So this code output hangs because here write ends parent process, and also child process doesn't close. You see, the pipe is shared by both parent and the child processes. Okay. The bullet 2, if some other process has the pipe open for writing, read will block, because it thinks that it write is going to wait for the write to happen. That's why it's hanging. It's not terminating, it hangs because they expect that the write would happen. Because here a write ends parent process, and also child process doesn't close. Because in anticipation of that, the it reads, but then it doesn't close because it anticipates that there is more write. See, the parent is writing and the child is reading, okay? So the parent will, the parent will write because, that fork system call, if it's greater than 0 is the parent, right? If it's 0, it's the child. And we're not checking for 0, for less than 0. We just assuming that it happens. But so else part is the child. The parent is the first part. So the parent writes and then does the wait. The child will read and so it reads the data that is in the pipe, and there is nothing here that it will terminate child. So when it reads the pipe, it's going to do, it's called hanging, because it expects that there will be more write to happen. Once again, going back to this picture, the two processes are sharing the same pipe. You remember the definition, you have APIs. Pipe in a new system call is a user space system, user space call. And then you make the call, it looks at the kernel layer, it's going to look at the table and identify which code is going to be. When you make a system call, you're making an interrupt, right? And there is an interrupt vector table at the kernel layer, which is going to look up and to see what code a pipe system call has been made, what code to be instructed for CPU to execute. And that is true with every system call, right? What you have is the API in your program. The actual implementation of the system call is the kernel layer, which is the space that communicates with the hardware. At the kernel, you have vector interrupt vector, which has a reference to what the call is, and has an index and a reference to which code has to be executed. Okay. So in this case, we have a pipe shared by both parents. So let's move on with this. I sent you this article here. Read it through. So hang means is not terminated. That means it's expecting the data to be written. In order to close the pipe, both child and parent have to terminate. Okay, folks, with that, I'd like to get into another topic. So these are two good examples of pipe system calls. He shows but one, what was the first one? A process with a pipe, one process that they can read, write to index 1 and then read index 0 of the pipe. Then here you have parent and child example. Okay, so let's move on with another topic. And the other topic is called, so I want you to give you may know it, I don't know. But so it's a numbering system. What we have is the binary, we have decimal, which is base 10. We have binary base 2, we have octo, which is base 8. We have hexadecimal base 10. I'm sorry, 16. Okay? So remember, everything that you do, your code gets executed in machine language. Machine language means binary, 0 or 1. So imagine you have, in your code, you have int a is equal to b. If a is equal to b, then do this, else do this. When you compile and link and so on, when it gets execution, it's all binary code, machine code. And I will show you machine code. You cannot make sense out of it easily. Okay? So the next thing is that is the assembly language. Assembly language is the next higher level of machine language, and assembly language programmers think like a machine. When you wrote, say, int a is equal to b, if a is equal greater than b, you don't think about machine. All you're thinking is the logical code, how to do it in English, right? But when you do write assembly language, you have to think of what the architecture of a machine looks like. It's not machine language, but it is very close to machine language. So you have to think of what I mean, the architecture, what CPU looks like, how many registers you have,